Hi, this is Mark Weitzman. Welcome to my YouTube channel, Theoretical Physics with Mark Weitzman. Today, I want to make some videos on the group theory in physics, Schensted Short Course. Before I get to the final lecture on Part 4, Applications of Quantum Mechanics, I want to go over some things that she covers in various addendums. She has addendum A, B, and C. So, so today we'll do Schensted Short Course, video 4i. I think I'll take 3 videos on this, and we'll cover addendums A, B, and C. And the idea is that some of these things are useful for the lecture 4, which is the final lecture in the short course. It's titled Applications to Quantum Mechanics. And I decided that to have a better understanding of this lecture when I make it, when I cover her 4th lecture, it'd be nice to go through some things in the addendums that would be needed. So let's just start with some things that may not have been defined that well or clarified that well for groups. So let's talk about conjugate elements and classes. Very important for finite groups. Actually, even for infinite groups. So 2 elements. Let's call them A and B of a group G are conjugate if and only if there exists a C in G such that A is equal to C, B, C inverse. And there's a lot of basic properties of this relationship, but the most important thing is that it's very easy to show, and I won't do it, but the conjugacy relationship is an equivalence class. And those of you who have had any kind of abstract algebra, you know what an equivalence class is. I'm not gonna define it here, and it partitions the group into disjoint conjugacy classes. So let me illustrate this. We have our usual group. So using our usual dihedral group of order 6. If you remember, and this is in the book a zillion times, but we have an equilateral triangle. Of course, I didn't draw that well. Then we have perpendicular or medians, bisectors, and let's label these lines L1, L2, and L3. So we have elements, the group G is equal to the set of E, which is the identity element, does nothing. C and C bar are clockwise and counterclockwise rotations. And sigma 1, sigma 2, sigma 3 are reflections about these lines that I've drawn, L1, L2, L3. And so in this group, the classes end up being we have three classes. I'm going to use set notation for them. I'm not sure if they always do that, but we have the set. The identity element always forms a conjugacy class by itself because, E is always equal to, any element in the group, E is equal to, G, E, G inverse. So E will always be conjugate to itself and not conjugate to anything else. Then the second class has two elements, and it consists of C and C bar. And this can be seen by, I just want to, for those of you who have the book or have the notes, you can follow along. If you go on my resources site and you look at Schensted's book, I think this is the actual book. Just have to find it for a second. Oh, let me, so this is Schensted's book, and yeah, here it is. So this is the dihedral group. This is the group multiplication table, and these will be representations I'll be referring to maybe a little bit later. But you can just follow along on the group multiplications here, or you can look at my my notes. I have notes on Schensted, and if you look at my notes, these are my notes. They're about half the size, but I sort of take the essential stuff from Schensted's book. And so here's again, this is the triangle, and here's the group. And so just by seeing, if you look at this, I can't show them both at the same time, but you can follow along. So CC bar, you can see that, for instance, sigma 1 C sigma 1 inverse is equal to, the sigmas are always their own inverses, sigma 1 C sigma 1 is equal to sigma 1 sigma 3, which is equal to C bar. So this implies that C is conjugate. I'll use the squiggle for the equivalence relation for conjugacy. So C is equivalent to C bar. And then you can show that, and you can do the same thing with C bar, and you'll get C. So, remember, equivalence relations are reflexive and transitive. So that gives us this element. Then the final class consists of sigma 1, sigma 2, and sigma 3. These form a class, and you can see that by C sigma 1 C inverse is equal to C sigma 1 C bar is equal to C sigma 3, so which is equal to sigma 2. So sigma 1 is equivalent to sigma 2, and then you can do C bar sigma 1 C bar inverse, which is equal to C bar sigma 1 C equal to C bar sigma 2, which is equal to sigma 3. So sigma 1 is equivalent to sigma 3, and then by the reflexive and transitive properties, you have all these elements are equivalent to each other. So basically, members of the same equivalence classes sort of have the same algebraic group properties, and they're just names. We have three different elements, and geometrically they're different, but algebraically they all have the same properties. They have the same, I'll just write down, same algebraic properties or group properties. So they have the same order, etc. Any equation, if you have an equation involving C, you can take sort of every element of C and replace it by C bar, and it will be valid. So, and these are very important, these classes, these conjugacy classes. And an invariant, let me make another definition before I give an important theorem. An invariant subgroup, sometimes called a normal subgroup, older terminology. Actually, normal subgroup is probably the mathematical terminology, and invariant subgroup is the physicist terminology. But invariant subgroup of a group G is a subgroup, let's call it squiggly B, script B, which consists of whole classes of G. So you can't just have part of a class for an invariant subgroup. You could have like E, C, and C bar. That would be an invariant, subgroup because it consists of the whole class. Of course, it has to be a subgroup, so it's always going to have the identity class in it. But otherwise, if it has one element of a class, it has to have all the elements of the class. And this implies that for all, let's say, for all, for all B in B and A in G, that A, B, A inverse is in B. I didn't write that well. Let me B. So this basically implies that when you have a normal group, like the usual abstract algebra terminology is that as cosets, A, B is equal to B, A. That's the same thing as, A, B, A inverse equal B. This is equivalent. So these are what's known as, these are normal groups or invariant groups, and you can, I didn't cover this is covered in the Schensted in the addendum, but I didn't cover the factor groups and isomorphism theorems. I don't think we'll have direct need for them right now, but eventually we might. But this comes in handy there. Okay. So one other thing I want to cover is a couple of other things in this video. Direct products of matrices. And Schensted uses a a very direct and sort of abstract definition, but I'm just going to just show you a simple example. Most of you have seen this in your quantum mechanics classes and everything, but let's say we have a 2 by 2 matrix, and I'll deal only with square matrices here. But let's say this is the matrix A, and then let's say we have a matrix B. I'll do a 3 by 3, even though it will be hard to put on all the elements. And this is defined by, and here you have to be a little careful because Z, for instance, Z's book, in his book on group theory, he uses the reverse definition. I'm going to give the one that's standard. You know, I've checked about 5 or 6 sources online, and almost everyone uses the one that I'm going to give here. But imagine multiplying the element A11 by the whole matrix B, A12 by the whole matrix B, A13. So these are 3 by 3 matrices. I'm sorry. Yeah, these are 3 by 3 matrices here. Then we'll have A21 times B, A22 times B, A23 times B. I'm sorry. See, I screwed that up. I always do that. Let me start again. It's going to be A11 times B, A12 times B, A21 times B, A22 times B. And just as an aside, this is equal to Z uses the opposite definition. Z says B11 times A, B12 times A, B13 times A. And, you know, you can just extend it. So he's going in the opposite order, but this is the standard one. Doesn't really make much difference, but you just gotta be, it's just rearranging the elements. And so this would be, for instance, a 6 by 6 matrix, and I'm just going to draw one part of it. So this just means A11, B11, A11, B12. I never have enough space. A13, B13, then A21, I'm sorry. A11 times this. Okay. Should be A11 times B21, A11, B22. Then I have another element here. Then I have A11, B31, A11, B32, and another element. And then you could, you know, this one's going to be A12, B11, and this is going to be A21, B11. This is going to be A22, B31. So it's all what you'd expect. Anyway, when you take these direct product of matrices, now you can get what's called the direct product representation. So if you have like gamma 1, let's say you have like gamma nu 1, let's say it's a nu 1-dimensional representation, times gamma nu 2. Then you take the matrices in the nu 1 representation and you multiply it, take the direct product with the matrices in the nu 2 representation. And this is another representation. In physics, we would put a circle around that. Schensted doesn't do it. But the important thing is that in general, this is reducible. And this is equal to some sum over AI gamma I, where gamma I is irreducible. So, in physics, especially in quantum mechanics, this is known as the Clebsch-Gordan series, or decomposition. Okay. Now, just to really confuse you, if you read in the book, you'll see that there's a different construction. It's similar, but it's different. Which is the direct product of groups. So if we have like two groups, say G1 and G2, which commute with each other, so G1, G2 is equal to G2, G1 for all G1 and G1 and G2 and G2. So in other words, the groups sort of like, they don't interact, or they're not related to each other. An example of this would be like a simple one, which is given in the book. We could have rotations. And we could have reflections. And in the sense, the dihedral group that we have is sort of a little bit like this, but I don't want to. But just in general, if you think of rotations in general and reflections in general, it really doesn't matter if you rotate first and then reflect, or reflect first and then rotate. You're going to get the same outcome. And so sometimes you want representations of the full group that it's orthogonal, the full orthogonal group that maintains distances between points. In the Euclidean plane, if we exclude translations, and we could include them too, but let's say we exclude translations for now, we only have rotations about a point, and we have reflections about that point. Those are the two things. And they both satisfy, they're both orthogonal transformations. They both satisfy O transpose O is equal to the identity. But rotations have the determinant of O equal 1, and reflections, they have the determinant of O equal -1. So anyway, this direct product group, so we're going to get a group which consists of, like, you have a huge infinite group. I know we're supposed to be doing finite groups, but sometimes we'll do infinite groups. You'll have rotations, R, by, a certain axis and a certain angle. And then you'll also have the rotation times an inversion. Inversions and reflections in 3 dimensions are basically the same thing. So it's like you double all the group elements. And the important, and then you can take the representation of this direct product group, and the only thing I will say is here, the representation of the direct product group are irreducible. And this is shown in the book. So that's what I want to cover in this part I video. In the next video, next 2 videos, I'm going to cover OA operators and projection operators. Like the OA operators and the 4 theorems, just and then projection operators. So I'll see you next time. Thank you very much.